You draw a perfect circle in the sand. I mean, it's the ultimate embodiment of order, symmetry, and simplicity. It's really just a single unbroken curve.
Right, it seems so incredibly basic.
Exactly. Yet, to mathematically describe that shape, to just simply find the ratio of the distance around it to the distance across it, you have to unleash an absolute monster.
A mathematical monster.
An infinitely long, entirely chaotic, totally unpredictable string of numbers. Pi. So today, we are taking a deep dive into humanity's 4,000-year obsession with this deceptively simple ratio.
It really is an obsession.
It is. And we're serving as your audio companion to the visual journey you're seeing unfold on screen right now. We're tracking this massive mathematical odyssey, starting with ancient engineers scratching shapes in the mud, all the way to quantum-era supercomputers processing trillions of digits.
And you see that right at the start of the visuals, that glowing, fiery pi symbol emerging from a perfect circle, just sort of exploding into the title. The paradox of pi is, well, it's one of the most fascinating stories in human history.
Because you'd think the universe would give us a clean, easy number for its most perfect shape.
You really would. But it absolutely refuses to. And chasing that number, it essentially forces the human mind to completely reinvent its own mathematical tools over and over again across millennia.
Okay, so let's unpack this from the very beginning. Because before pi was this, universal constant floating around in modern physics textbooks, it was a totally practical physical problem.
Very physical. We're talking roughly 1900 BC here.
Right, so ancient engineers who didn't really care about the philosophical secrets of the cosmos, they just needed to build grain silos and temples and wheels that actually rolled properly.
Exactly. If you need to build a circular silo, you really need to know how much material it takes to go all the way around the outside. But measuring a curve is notoriously difficult.
Because rulers are straight.
Right. So the ancient Babylonians, they realized they could approximate the curve by using straight lines, which they could actually measure. And we see this on the Susa tablet in the visuals. They took a regular hexagon and drew it perfectly inside a circle.
Just a straight-edged hexagon tucked inside.
Yes. And since a hexagon is just, well, it's just 6 equilateral triangles pieced together, they knew the perimeter of that hexagon was exactly 3 times the diameter of the circle.
So they knew the circle's perimeter had to be just a little bit more than 3 times its diameter.
Right, because the circle bulges out just slightly past those straight lines. And by comparing the slight difference between those straight hexagonal lines and the curved circle, the Babylonians estimated pi at 3.125.
Which is exactly 3 plus 1/8.
Yep, 3 plus 1/8.
Which is actually incredibly close for Bronze Age engineering. But the conceptual leap here is what's so interesting to me. It's sort of like trying to measure a flowing, curved river using rigid, straight rulers.
That's a great way to put it.
You can't just bend a wooden ruler around the river bend. So you lay down a bunch of straight rulers in a jagged line and just say, close enough. They didn't have algebra. They were just trying to get the architecture right.
And this establishes the foundational human approach to circles.
Yeah.
If you want to understand a curve, you compare it to straight-edge shapes you already understand.
Right.
And a few hundred years later, around 1650 BC, we see a slightly different approach from the Egyptians. There's this scribe named Ahmes, and he recorded a method on what we call the Rhine papyrus.
Oh, this is the part on screen where the circle literally morphs and reshapes into a square. Right.
Exactly. They conceptually tried to morph a circle into a square to compare their areas. They imagined a circle with a radius of 4.5 units sitting on a 9x9 grid, and they mathematically reshaped it into a square with a side length of 8 units.
Okay, so a 9x9 circle to an 8x8 square.
Right. And by comparing the areas of those two shapes, they implicitly calculated a value for pi of roughly 3.16.
3.16. So again, getting really close. And they didn't have the equation area equals pi times radius squared, like we learn in school today. They just had this physical geometric intuition.
It's all visual and physical for them. But to move past these rough architectural estimates, humanity really needed something more rigorous. They needed a repeatable algorithm.
And that requires a major shift from practical measurement to theoretical mathematics, which brings us to my favorite ancient Greek, Archimedes of Syracuse, around 250 BC.
Archimedes is just brilliant. He invents what we call the method of exhaustion, and the visuals here are stunning. You see these polygons with exponentially increasing sides squeezing the circle.
Yeah, that extreme macro zoom on the microscopic gap between the shapes. So cool. So how did his algorithm actually work?
Well, Archimedes knew that a polygon drawn inside a circle, inscribed, will always have a perimeter slightly less than the circle itself.
Because it's trapped inside.
Right. And a polygon drawn outside of the circle, circumscribed, will always have a perimeter slightly greater. So he mathematically trapped pi between those two boundaries.
He squeezed it.
He squeezed it. He started with a 6-sided shape, then doubled the sides to 12, then 24, 48, and finally up to 96 sides.
That is a lot of sides to draw.
It is. And the shapes hug the circle tighter and tighter, getting microscopically close to the true curve. By calculating the perimeters of those 96-sided polygons, he proved mathematically that pi had to live in the tiny gap between 3 and 1071 on the low end and 3 and 17 on the high end.
Okay, I have to push back here, though. If this squeezing algorithm is conceptually perfect and he just keeps doubling the sides to get a tighter squeeze, why stop at 96 sides?
Right. Why not go further?
Exactly. I mean, 96 is a lot, but if the logic goes on forever, why not push it to 1,000 sides? Did Archimedes just, get tired?
Well, it comes down to the absolute agony of ancient arithmetic.
Yeah.
You really have to remember the tools he was working with. Archimedes didn't have calculators. He didn't have decimals.
Right.
He didn't even have our modern numeral system with the placeholder for zero. He was doing this entirely with Greek letters representing numbers.
Oh, wow. I can't even imagine.
It's brutal. Every single time he doubled the size of the polygon, he had to use the Pythagorean theorem, which requires calculating square roots.
Oh, no.
Yeah, he was manually extracting square roots of massive, clunky fractions by hand. He simply hit the physical limits of manual computation for his era.
So his brain just hit a hardware limit, essentially.
Basically, yeah. But conceptually, he proved the method. He proved that you could theoretically double those sides forever to achieve any desired accuracy.
It's just a massive amount of sheer grinding brain power. And actually, European mathematics kind of stalls out on this for a long time. The next major leap in the quest happens in the East.
Specifically in China.
Right. Around 265 AD, a mathematician named Liu Hui looks at Archimedes' 96 sides and decides to push the boundary to a staggering 3,072-sided polygon.
And you see this on the grid in the video. He calculates the areas using these tiny microscopic rectangular slivers. And he achieves an accuracy of 3.1416.
Which is a monumental feat of endurance. But then another Chinese mathematician, Zhu Chongzhi, comes onto the scene in the year 480 AD and pushes it even further.
Way further. Zhu pushed the polygon method to 24,576 sides.
Over 24,000 sides. That is just absurd.
It is. He locked down pi to 7 decimal places. And through this, he discovered a specific fraction, which on screen you see collapsing on that high-resolution number line. It's 355 divided by 113.
The Milieu fraction.
Yes, the Milieu fraction.
Yeah.
That simple-looking fraction is so insanely accurate it matches pi out to 6 decimal places that nobody anywhere in the world would find a better approximation for over 900 years.
And here's where it gets really interesting for you listening. Think about how he did this. We just talked about the agony of Archimedes' arithmetic. Zhu Chongzhi was doing calculations requiring hundreds of complex square roots, maintaining precision up to 9 decimal places.
Right.
And he didn't have a pen and paper. He was doing this with a pile of wooden counting sticks.
It's almost unbelievable.
He was laying out physical wooden sticks in intricate grid patterns on the floor just to keep track of these massive algebraic operations. I mean, it's the ancient equivalent of trying to render a 4K video using an abacus.
That is a perfect analogy. It is an absolute testament to human willpower.
Truly.
But Zhu Chongzhi's 24,000-sided polygon also highlights a looming wall in mathematics. Because eventually, adding more sides to geometric shapes becomes physically and practically impossible.
Yeah, a 24,000-sided polygon already looks exactly like a perfect circle to the human eye anyway.
Exactly. To move forward, mathematicians had to abandon drawing shapes entirely. They had to stop thinking about geometry and embrace the abstract concept of infinity.
Which is a massive paradigm shift. And that shift happens in India around 1350 AD. Enter Madhava of Sangamagrama and the Kerala school of mathematics. They completely ditch the polygons.
You do. Instead, they turn to trigonometry and something called infinite series expansions.
And the visual for this is so striking. The graph of the arctangent function with the Taylor polynomials progressively wrapping around and hugging the curve.
It's a monumental breakthrough. Centuries before calculus is formally invented in Europe, Mother realizes that you don't need to draw literal shapes to find pi. You can find it through an infinite, never-ending addition and subtraction of fractions.
So what does this actually look like in practice? Instead of drawing literal shapes, they're now just crunching a never-ending sequence of abstract fractions.
Think of it like trying to perfectly mold a piece of clay over a complex curved surface. Instead of using one big clunky piece of clay, you use an infinite number of thinner and thinner layers.
Okay, I follow that.
Mother showed that pi divided by 4 is exactly equal to 1, minus 13, plus 15, minus 17, plus 19, and so on, alternating plus and minus forever.
So the philosophical shift here is huge. Humanity is moving from the finite physical world of geometry to the infinite abstract world of analytical series. They accept that perfection can't be reached in a single calculation, but it can be endlessly approached.
Endlessly approached. That is the exact mechanism of the shift. But there is a major mathematical catch with this specific series.
Right, because that specific series 1 minus a third plus a fifth, it converges on the true value of pi agonizingly slowly.
So slowly.
If you just add those fractions one by one, you have to add up hundreds of thousands of them just to get a few accurate decimal places.
And Matava knew that. It was way too slow to be practical.
Which is why his absolute genius shines in his invention of what we call correction terms.
Okay, what is a correction term?
He figured out that you didn't actually need to calculate the next 100,000 fractions manually. He built a mathematical shortcut. He discovered algebraic formulas you could just tack onto the end of a partial series that would instantly approximate the remaining infinite tail of fractions.
Oh, wow. So he's fast-forwarding the calculation.
Exactly. Using these correction terms, he quickly achieved 13 correct decimal places of pi.
It's mind-blowing. He essentially figured out how to mathematically jump ahead in line. Okay, let's fast forward a bit. When this includes.
And right around that same time, you have one of the great tragic comedies in math history. A Dutch mathematician named Ludolf van Zeulen in the late 1500s.
Oh, Ludolf.
He apparently didn't get the memo about infinite series or nested radicals because he dedicates his entire existence to the old grueling geometric exhaustion method.
The Archimedes methods.
Exactly. Ludolf calculates a polygon with 2 to the power of 62 sides. That is over 4 quintillion sides.
Just let that number sink in.
It's absurd. He spends his entire life doing this by hand. He eventually gets 35 digits of pi, and he's so proud of this lifelong grind that he literally has those 35 digits carved directly onto his tombstone.
And you see that glowing tombstone in the video. It became known as the Ludolphine number in Germany. It's a heroic effort, but it is also deeply tragic because it represents the absolute dead end of brute force geometry. Because shortly after he dies, Isaac Newton invents calculus.
And Newton just flips the table.
He really does.
We see the Riemann rectangles sweeping under a binomial curve on screen. Newton uses his newly invented binomial theorem in calculus to generate infinite series that converge incredibly fast. Instead of spending a lifetime drawing quintillions of sides, Newton casually calculates pi to 15 digits in a matter of days.
The tools of calculus changed the landscape permanently. Newton famously wrote a letter saying, and I quote, "I'm ashamed to tell you to how many figures I carry these computations, having no other business at the time."
It's almost painful. I mean, Ludolf dedicates his entire existence to getting 35 digits with polygons, and a few decades later, Newton knocks out 15 digits in his spare time and feels embarrassed that he was procrastinating.
It really is a tragedy. And by 1706, an astronomer named John Machen took these calculus tools even further.
Right, you see his infinite series expanding rapidly on screen.
He used a highly refined arctangent formula. It was a much faster evolution of what Madhava was doing in India centuries earlier. And Majund used it to just blast past the 100-digit mark. The speed of computation was now growing exponentially.
And suddenly, pi starts showing up.
Incredible power of the infinite series finally reaches Europe. It collides with the Renaissance and the invention of calculus. And it sparks a massive explosion in computational speed. The 1590s through the 1700s are just a wild time for math.
We see the French mathematician Francois Viette create the first exact analytical formula for pi. But instead of adding fractions, he uses an infinite chain of nested square roots.
Right, you see that infinite tree of nested radicals on screen converging
Ah,
towards a value.
yeah.
Square roots inside of square roots, inside of square
Up everywhere, not just in circles. In 1735, Leonhard Euler shocks the world by solving the famous Basel problem.
This is a beautiful moment in math.
It really is. The visuals show 3D spheres and complex planes connecting prime numbers to the sine function. Euler proves that if you take the inverse squares of all whole numbers, 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared out to infinity, they perfectly add up to pi squared divided by 6.
Which is a massive revelation. It proves that pi isn't just a geometric quirk about circles. It is baked into the fundamental fabric of number theory, prime numbers, and probability. It is structurally foundational to mathematics itself.
So the digits are piling up at breakneck speeds. 100 digits, 500 digits, 700 digits. But as mathematicians keep digging deeper into this endless string of numbers, a new realization dawns on them. Finding the end of pi is a fool's errand.
Because there is no end.
Exactly. The real question wasn't what is the last digit. The question was about the fundamental nature of the number itself.
Right, and you see this in block 7, where the number line fractures and equations just shatter on screen. In 1761, Johann Lambert proved that pi is an irrational number, meaning its decimals never repeat and never end.
But then the final crushing blow came in 1882.
Yes, when Ferdinand von Lindemann proved that pi is a transcendental number.
Transcendental, it sounds so mystical. Let's unpack what that actually means in the math world, without the textbook jargon.
Basically, when we say pi is transcendental, it means it is completely immune to standard algebra.
Immune to algebra.
Completely. You cannot write down a finite algebraic equation using normal rational whole numbers, no matter how complex, no matter how many additions, subtractions, multiplications, divisions, or square roots you use, and have the exact answer be pi. Pi transcends the very language of finite algebra. It cannot be the root of a polynomial equation. Question to bring us into the modern era, the machine age. We didn't keep calculating pi to find an end or to solve a geometric puzzle. We kept calculating it because generating the digits of pi became the ultimate stress test for humanity's newest invention.
The computer.
The computer.
So it shifted from being a mathematical mystery to a raw benchmark for processing power.
Exactly. The era of human calculation ends in 1949. We see the dawn of the machine in the visuals. Glowing vacuum tubes, punch cards, and a massive mechanical counter ticking wildly.
The ENIC computer.
Yes, the ENIC calculated 2,037 digits of pi in 70 hours. What used to take a human being a lifetime of grinding arithmetic, like poor Ludolf, now took a machine a long weekend.
But the algorithms themselves completely changed too, right? We weren't just feeding Newton's linear formulas into computers.
No, because even a computer would get bogged down eventually with a slow linear series. It is the ultimate expression of the human drive to know. I mean, consider the progression we've just tracked in this deep dive.
It's wild.
From ancient engineers scratching straight lines in the muddy banks of Babylon using hexagons, to Zhu Chongzi painstakingly laying out thousands of wooden sticks in China.
To the abstract infinite series of the Kerala School in India.
Right, and all the way to modern supercomputers processing billions of digits in a sweltering apartment. Pi mirrors humanity's growing capacity to grasp the infinite. We evolved our tools from the physical to the abstract to the computational.
It is a 4,000-year relay race. And as our deep dive comes to a close today, I want to leave you with a final mind-bending thought to mull over on your own. We've established that the digits of pi 3.14159, on and on for trillions of digits, appear perfectly random. They are mathematically chaotic, they never repeat, and they are totally unpredictable.
The ultimate chaos.
Yes, but that chaotic, infinite string of numbers perfectly describes the most ordered, symmetrical, predictably simple shape in the entire universe.
The circle.
It's the ultimate paradox.
So, for you listening, think about this. Could this chaotic, never-ending sequence of digits actually contain the foundational code, the hidden fingerprint to reality itself? Or is it just the ultimate numerical mirage, tricking us into looking for a bottom to a well that we know has no end? Keep your eyes on that circle. It clearly still has plenty of secrets left.